All right, so for this lesson, we're going to build on an existing game section. So before going into this, make sure that you've already done this section. So this is PrepTest 64, the games section for that lesson. You should be able to find this under this lesson in your student account. And yeah, once you've completed this section, and then go through the whole process, complete the section, review it, make sure you understand everything about how to approach the section, and then feel free to come back here and resume. All right, so here we're going to focus on these rule replacement questions that you'll occasionally get on the game sections. Now, the questions themselves will say something like this: which of the following, if substituted for a certain rule, would have the same effect on the game? It's worth noting these are not especially frequent questions, but they're pretty consistent. Usually, probably a good majority of the game sections in recent years have had one or two of these rule replacement questions in them. Now, they can be a little bit intimidating at first if you're not used to them, but once you do get used to them, they're really not that bad. Though, as far as the question itself is concerned, it's worth noting that when LSAT asks you for something that would replace one of the original rules and it would have the same impact on the game, it's actually asking you for two slightly different things. In order to have the same impact on the game, there's basically two criteria that need to be met. Now, the first criterion is a little bit more obvious. When the question is asking you for something that would have that same effect, you want to make sure that the right answer choice is actually going to maintain the original restriction. And again, that's a little bit more obvious. When the question here, for example, asks you what would have the same effect as X must be interviewed before Z, you want to make sure that the right answer choice will actually ensure that X is going to go before Z. That said, though, it's worth noting that that's only half of it, and not every answer choice that would ensure that restriction would necessarily be correct. Because in order to have the same impact on the game, you want to make sure that the answer choice that you're looking at doesn't go too far, that it doesn't restrict the game beyond what you already have. In fact, a good way of kind of looking at that is that when you're looking at the answer choices is to simply consider whether an answer choice always had to be true as far as the original rules were concerned. Because if you're looking at an answer choice that didn't always have to be true, that would effectively mean that if you implemented that as a rule, you would be restricting the game further than what you already had. So let's take an example. Say you had that game, essentially 6 positions, and you have this rule that says that X has to go before Z. And say one of the answer choices said something like, X must always go first. Now you'll notice that this answer choice, it would meet the first criterion here, which is that if we implemented that X must always go first, it would get the job done. It would ensure that X is always before Z. But would that make it a good answer choice? Well, no, that wouldn't be enough, because you'll notice that chances are this answer choice would end up failing the second criteria, which is, did it always need to be true? And chances are in this game, X didn't always have to go first. Chances are X could have gone into some other positions as well, as long as it was before Z. So this answer choice would pass the first criterion by saying that X is always first. It would ensure that it's always going to go before Z, but it goes too far, because if X could have gone into some other position, then this wouldn't have the same impact. This answer choice goes much further than the original rule would have required. On the other hand, say an answer choice said something like, X can never be last. You'll notice that this answer choice, this would meet the second criterion, but it would fail the first one. This is an answer choice that always had to be true. If X was before Z, well then yes, naturally, it could never go last. But if we implemented this as a rule, if we said that X can never go last, that wouldn't have the same impact, because that wouldn't ensure that X goes before Z. Answer choice B would allow for X, for example, to go into the 5th position, while Z could have gone prior, and so that's no longer the same effect. So answer choice B would also be a bad answer choice, but for the opposing reason. It's something that always had to be true, but doesn't get the job done. A good answer choice will meet both of the criteria. It'll be something that will ensure the original rule will be maintained, and it's going to have to be something that always had to be true. And of course, the question now becomes, what would that look like? What would a good answer choice look like here? Now, usually, a good answer choice is going to play off of other things that are going on in the game, some of the other rules as well. But let's do that. Say we had kind of a broader setup here where we have these 6 elements in play. But now we're going to add that the TW apparently had to go before X, and then S had to go after the TW block, and the Y had to go before the S. Now, let's assume that the question was still the same. So the question is going to ask, what would properly replace this rule that X has to go at some point before Z? Now, a good answer choice might say something like this. S and Y are the only employees that can be interviewed after Z. Now, you'll notice that, let's go through the step by step. Is this something that would ensure the original restriction would be maintained? And you'll notice that it would. If we say that S and Y are the only people that can go after Z, well, that would mean that everybody else, including X, would have to go before Z. So by saying that S and Y are the only people that can go after Z, that would ensure that X has to go before Z. Now, there is the other question, though, which is that, did this always have to be true? Did it have to be true that S and Y were the only people that could have gone after Z? And actually, yeah, it is, because the only other remaining elements here are T and W, and you'll notice that T and W would have had to go before the Z regardless, so they couldn't have gone after Z. So it would be true to have said that S and Y are the only people that could have gone after Z. So in other words, this answer choice is one that ensures that X goes before Z, and it's one that always had to be true. Answer choice C would have been a viable answer here. All right, so for this exercise, we're going to be building off the first game in PrepTest 64. Now, again, presumably you would have already done the game section from PrepTest 64. So we're just going to work off of that first game. This is the game regarding the parking spaces. Now, in terms of the setup, ideally, you should have had something that roughly looks like this. Essentially, you would have had 6 slots to work with. There are 6 people, each of which will go exactly once into one of those 6 positions. And in terms of the rules themselves, roughly this would have come down to a set of rules that tell you that T has to go before Y, which itself has to go before R. Eventually, we were told that R had to go into the first 4 positions, but really that just translated into either 3 or 4, because we know that R can't go into 1 or 2 since it's after T and Y. Now, separately, there was also a rule about S having to go before X. Now, this next step might not be something that you had to do, but it's not a bad idea to exhaust this game. And what we can use essentially is the R having to go into either positions 3 or 4. And from there, you should have had something that roughly looks like this. So if R goes into 3, then T and Y would have been stuck in positions 1 and 2 respectively. And then in terms of these 3 positions, we don't know much more. It's a little bit more open. And if R ended up going into position 4, then to be honest, we didn't know much more. T and Y obviously would have gone somewhere among these 3 positions, but we don't know exactly where. And then you had the other guys, V, S, and X, which had a little bit more flexibility. Now, one of the questions in the game should have led you to one minor deduction that you should have been able to make, which is that it ends up being the case, and that's just useful to know for some of the questions that we're going to do, that X ended up having to go into either positions 5 or 6. This isn't a deduction that you necessarily had to make up front. Most people probably don't, but by the time that you got to the relevant question, this would have been key to answering the question. This is something that you figure out as you go. And yeah, X ends up having to go into either 5 or 6, because in the top scenario, I mean, obviously X couldn't go into 4 because S had to go before the X. And in the bottom scenario, you'll notice that X also couldn't go into the first 3 positions, because if it did, then, well, you would have had to have the S before it, and that would have taken up 2 of these spaces, and then you would not have had enough space for both T and y. So x, no matter which way you went, would have ended up having to go somewhere between positions 5 and 6. Now, the way this exercise is going to work is you'll have these rule replacement questions given to you, but it's worth noting that of the answer choices, more than one can be a viable answer here. So you're not just looking for one correct answer, you're just looking for whichever ones happen to be viable answer choices to answer the question. So you're not just limited to one correct answer choice here. Take a look at question number 1, see what you can do with this on your own first, and then feel free to resume when you're ready. All right, so let's take a look. So the question itself is asking, which of the following, if we substituted it for the rule that R has to go into the first 4 positions, would have the same impact on the game? And really, when it says that, the first 4 positions, functionally, that just meant the 3rd or the 4th position. So the question is basically, what would replace this rule right here that R has to either go into 3 or 4? Let's take a look. Answer choice A. R must be assigned to a lower numbered parking space than X. Now, one thing that's worth noting is you'll notice answer choice A did have to be true. In fact, we do know that R had to go lower numbered than X because, as we said, X ended up going into positions 5 or 6, and no matter what, R was lower numbered. So this does kind of pass that test. It does pass the test of, did it always have to be true? But of course, there is the other side of the question, which is, would this get the job done? Say that R has to go lower numbered than X. Would that ensure that R goes into the 3rd or the 4th positions? And you'll notice that that wouldn't, because when you say that R has to be lower numbered than X, that easily would allow for R to go into position number 5, and then X can go into position number 6, and that would still work. So answer choice A is not a viable answer here because essentially it doesn't get the job done. It doesn't ensure that R will be in positions 3 or 4 at all times. Answer choice B. R must be assigned to a lower numbered space than S. Now, this, you'll notice, kind of goes the other way. If we said that R has to go lower than S, well, the thing is, S has to go before X. So if R had to go lower than S, then that would mean that it could never go into positions 5 or 6. And that would arguably get the job done. That would ensure that R is going to be stuck in the first 4 positions, or I suppose more specifically in 3 or 4, because it still obviously has to go after T and Y. But there is the other side of the question, which is, did that always have to be true? Did R really have to go lower numbered than S? And you'll notice that it didn't. R easily, for example, in the second scenario, we could have had an S somewhere among these 3 positions, right? You could have done something like S, T, and Y, and then X and who's left, X and V could kind of just shuffle between 5 and 6, and that would have worked. So you'll notice that answer choice B, even though it would have gotten the job done, it would have ensured that R is stuck basically in the first 4 positions, it never had to be true. R didn't have to go lower than S, so implementing this as a rule would have gone too far. So B is not a viable answer. Next, C. R cannot be assigned to parking space 5 or 6. Now, this is kind of an easy pickup. In fact, we'll call these kinds of answer choices inversions. Essentially, instead of saying that R has to go into the first 4 positions, this is just kind of inverting that by saying that R can't go into the other positions, which, of course, will have the same effect, right? If you say that R can't go into 5 or 6, well, then it'll have to go into 1, 2, 3, or 4. And it always had to be true. R couldn't go into 5 or 6, so this would have been a viable answer. Next, answer choice D. If X is assigned to parking spot number 5, then R must be assigned to parking spot number 4. Now, with these kinds of answer choices, you always want to be cautious. Specifically, when I say these kinds of answers, I mean conditionals, right? If X happens to be in 5. Because the thing is, if X was in 5, then yes, this answer choice would ensure that R is going to be among the first 4 positions. But the problem is, answer choice D only tells you what happens if X is in 5. But we need to make sure that R is always going to go among the first 4 positions. And you'll notice that answer choice D, does it tell you what happens if X wasn't in 5? And no, it doesn't. So answer choice D would easily allow for the possibility that if x was in 6, for example, then r could have gone into 5, and then that wouldn't be good enough. That would not ensure that r has to go among the first 4. There's also the other half too, which it fails. Answer choice D isn't actually true either. If x was in 5, r never had to go into 4. For example, in the top scenario, we could have had x over here in 5, and then r could have just as easily gone into 3. So answer choice D actually fails on both counts. This never had to be true, and even if it was true, it wouldn't be good enough to say that r is always going to go into positions 3 or 4. So D is out. E. The only employees that can be assigned to parking spaces 5 and 6 are V, S, and X. Now, answer choice E is another one of those examples of what we'll call inversions. Basically, what's happening here is that instead of saying that R has to go into the first 4 positions, this is basically saying that the only people that can go into the other positions, 5 and 6, are just everybody else. Which, if you think about it, that does get the job done, right? If we say that the only people that can go into 5 and 6 are V, S, and X, that certainly means that R cannot go into 5 and 6, so R gets stuck in the first 4 positions. Now, the other side of this, did that have to be true? Did V, S, and X, were those the only people that could go into 5 and 6? And incidentally, you'll notice that that did also have to be true as well, because we know that the other people that remain are just T, Y, and R, and T, Y, and R never could have gone into 5 or 6 anyways. So answer choice E, that had to be true. The only people who could have gone into 5 and 6 are V, S, and X. And moreover, if this is true, then that certainly precludes R from going there, so R ends up getting stuck in the first 4 positions. This had to be true, and it gets the job done. Next, answer choice F. If S is assigned to a parking spot lower than 5, then R must also be assigned to a parking spot lower than 5. So again, with conditional statements, you always want to be cautious around the fact that it's if that is true. But yeah, let's follow through. This is telling us that if S is lower than 5, then R would also be lower than 5. And that, in that instance, if S is lower than 5, that would get the job done, because then it would make sure that R has to go lower than 5, so it will have to go among the first 4 positions. But then the other concern is, what if S wasn't lower than 5? Well, it's worth noting that if S wasn't lower than 5, then the only other possibility is that S would have to go into 5, because S had to go before X. And you'll notice that if you put S into 5, then you would end up with X in 6. And so R would actually still end up in the first 4 positions. So answer choice F, it looks like it does get the job done. Basically, F means that anytime S is lower than 5, then R would be in the first 4 positions, which is what we want. And if S wasn't lower than 5, then R would still end up in the first 4 positions, because then S would be in 5, and then X would be in 6, and that's exactly what we want. Now, the other half of this whole thing is, did that have to be true? And yeah, this one's a little bit easier here, because we know that R was always lower than 5. So it always had to be true that if S is lower than 5, as well as otherwise, R would also be lower than 5. This always had to be true, and it gets the job done. Next, answer choice G. R cannot be assigned to parking space 1 or 2. Now, that's technically true. R couldn't have gone into 1 or 2 because R had to go after both T and Y. But does it get the job done? And no, in fact, this doesn't actually add anything that we didn't already know. This doesn't restrict R beyond the fact that, R has to go after Y and T. So this doesn't get the job done. Saying that R can't go into 1 or 2 still leaves it open to go into 5 or 6. So the viable answer choices to question number 1 happen to be C, E, and F. Next, question number 2. Once again, take a moment, see what you can do with this on your own first, and resume when you're ready. All right, so what do we got? The question, which of the following if substituted for the constraint that Y has to be a higher number than T? So specifically, we are replacing this rule right here that basically T is before Y. Let's see what we can do. Answer choice A. V and S are the only employees that can be assigned a lower numbered space than T. Now, let's start with, if that was true, would that get the job done? And arguably, yeah, it kind of would, wouldn't it? Because if V and S are the only people that can go lower than T, well, then that means that everybody else has to be higher than T, which includes Y, so it would ensure that Y is going to have a higher number than T. That checks out. But of course, there's the other half of it, which is, did that have to be true? Were V and S the only people that could go lower than T? And actually, yeah, they were, because Y and R obviously had to be higher than T, and X ended up getting stuck in 5 or 6, so X was still always higher numbered than T. So this gets the job done, and it always had to be true. So answer choice A is viable. Next, answer choice B. If Y is assigned to parking space 2, then T has to go to parking space 1. Well, one thing that should kind of concern you right away is this only tells you what happens if Y is in 2. Now, according to B, if Y is in 2, then T would be in 1, which is great. It would ensure that T would go before Y. And technically, that also had to be true, because if Y is in 2, it's always true that T would have to go into 1. But, of course, there's the other half of the condition. What if Y wasn't in 2? Does answer choice B really tell us what would happen? And you'll notice that it doesn't, right? In other words, answer choice B could easily allow for the possibility that Y could, for example, go into position 1, and then T can do whatever it wants, right? So answer choice B would not be good enough. It doesn't get the job done because it really only tells you what happens if Y is in 2. But we need this rule to hold regardless of where Y might have gone. So answer choice B is out. C. Robertson must be assigned to a higher number than T. Now, these kinds of answer choices can often be tempting, but you'll notice that this wouldn't be good enough. This would not ensure the initial restriction would exist, because what this would do, this basically says that R has to go higher than T. And to be fair, we had another rule previously that R was higher numbered than Y, but that doesn't really tell you anything about what happens to Y and T. So R is higher numbered than Y. You'll notice that T and Y can kind of shuffle here back and forth. So answer choice C isn't good enough. It doesn't ensure that T is going to be below Y. It will just make sure that both of them are below R, but we don't know what sequence. So answer choice C is out. Next, answer choice D. Susan must be assigned a higher number than T. Now, actually, so from the get-go, it's worth noting this never had to be true, did it? Because S didn't have to go higher than T. S easily could have gone lower than T. In fact, we could have had S right here in position number 1, and then we would have had T and Y in 2 and 3, and then V and X could have done whatever. So answer choice D never had to be true, and that's a good enough reason to get rid of it. For the record, I'm also not sure that it would get the job done, because even if S was higher than T, that still doesn't tell you much about Y and T and how those would relate, so this would probably fail on both counts. Next, answer choice E. V must be assigned a higher number than T, but lower than Y. Now, this also never really had to be true, did it? Because V never had to go higher than T. V is also one of the elements that could have gone into position 1. You could have easily had V, T, and Y, and then S and X could have gone into 5 and 6. So that's a good enough reason to get rid of answer choice E. For the record, though, this answer choice would have gotten the job done. This would have actually ensured that T would have gone before Y. The reason for that is, if you say that V is higher numbered than T, but lower than Y, well then yeah, T would end up going before Y. So this would have ensured the restriction. It just never had to be true. It just goes too far. So this is still not a good answer. Next, answer choice F. Unless T is in 1, then Y must go into 3. So this is basically saying, just to kind of simplify this a little bit, because unless can be a little bit messy, we can replace the unless with if not. So this basically reads, if T was not in 1, then Y would have to go into 3. And that's true, because if T was not in 1, then T would have ended up in 2 previously. And if T was in 2, then Y would have ended up in 3 because Y would have had to go later. So this did have to be true. The other half of this is, though, would this get the job done? Would this ensure that T goes before Y? And this is a bit tricky, but it wouldn't. The reason it wouldn't is that if t was not in 1, without this rule that we are replacing, if t is not in 1, we don't actually know where it would end up going. If t is not in 1, it could have gone anywhere. So for example, in this situation where t is not in 1, you could have just as easily ended up with t in 5. Now, according to this, y would still have to go into 3, but that wouldn't ensure that t is before y. So answer choice F does not get the job done. Answer choice G, the only employees that can be assigned parking space 1 are T and V. Now, this didn't actually have to be true, did it? Because when you say that the only people who were in 1 are T and V, S could have gone into position 1 as well. So this isn't good enough, this never had to be true, rather, which is a good enough reason to get rid of answer choice G. For the record, I'm pretty sure that this is also not good enough either, because when you say that the only people that can go into 1 are T and V, that allows for V to go into 1, and if V is in 1, that leaves T and Y to do whatever. So there's no it doesn't ensure that T would go before Y. So it looks like the only viable answer for question number 2 here is answer choice A. Next, let's take a look at 3. Once again, see what you can do with this on your own first, and resume when you're ready. All right, so once again, let's start with the rule itself. So the rule is that which of the following is substituted for the rule that x has to be higher than s? So essentially, we are trying to replace this guy right here. Let's take a look. Answer choice A. X has to be assigned to parking spaces 5 or 6. Now that definitely had to be true, right? We kind of said that up front. X has to go into one of these two positions. But does it get the job done? And you'll notice that it doesn't. When you say that X has to go into 5 or 6, that fully allows for the possibility that X could have gone into 5 and then S could have gone into 6. So answer choice A isn't good enough. Next, answer choice B. Only V can be assigned to a parking space higher than X. Now, is that true? Is it true that V is the only person that could have gone higher than X? And actually, technically, yes, because we know that T, Y, and R were always stuck somewhere in the first 4 positions, and we know that S always had to go before X, so the only person left who could have gone higher than X was, in fact, V. So that definitely had to be true. And then the other half of this is, would it get the job done? And actually, yeah, because if V is the only person that can go higher than X, well, that means that S would have to go lower. So this always had to be true, and it gets the job done. B is a viable replacement. Next, answer choice C. If V is assigned to 5, then X would have to go into 6. Now, technically that's true. We do know that if V is in 5, X would have had to go to 6 because X was stuck between position 5 and 6. But the real question is, does it get the job done? Does it ensure that S will go below X? And no, in fact, this is the conditional issue. Answer choice C only tells you what happens if V happens to go into 5. But what if V wasn't in 5? Answer choice C doesn't create any restriction because V can go anywhere, right? So you could have had V in number 1, and now S and X are free to do whatever. So answer choice C doesn't get the job done. It had to be true, but it's not good enough. Answer choice D. S must be assigned to the first 4 positions. Now this one's a bit of an easy knockoff because we know that that's just not true. Previously, we could have had S in position 5 and X in position 6. So since D never had to be true, this is out. Answer choice E. Neither V nor S can go into 6. This also never had to be true. We know V could have gone into 6, which is a good enough reason to get rid of it because that never had to be true. Next, answer choice F. X must be assigned to 5 and V in 6 unless X is in 6. So this one's a bit of a messy one, but you'll notice that this does end up working because this is basically saying that if we don't, again, we can do an if not here. This is saying that if we don't have X in 6, then you're going to have X in 5 and V in 6. So this basically just gives you 2 possibilities. Either you have X in 6, in which case S is easily below, so that's fine. Or alternatively, you would have had to have X in 5, and then V would have had to go into 6, which, first of all, that would ensure that S is going to go lower, because if X is here and V is here, then S is going to be somewhere in the first 4 positions. And it did actually have to be true, because any time that X wasn't in 6, the only other possibility was that X would end up in 5 and V would end up in 6. So answer choice F is a viable answer here. Lastly, G. At least 4 of the new employees must be assigned parking spaces that are lower numbered than X is. Now, this technically is true because we said early on, X has to go either in 5 or in 6, which means, well, at least 4 people would be lower numbered than X. But the other question is, does this get the job done? Does this ensure that S will be lower numbered? And no, because this would easily allow for X to go into 5 and then S could go into 6, which would not ensure that S is lower numbered than X. G is not a viable answer. All right, so we're going to try this again with another game. Specifically, we're going to use the third game of that set. This is the bike testing game. Now, in terms of how to set up this game, there arguably could have been 2 ways that you could have gone about this. You could have set this up based on the bikes or based on the people, both of which are actually reasonable setups. One of them ends up working a little bit better due to one of the rules, but it's kind of hard to see that up front. But what you could have done here is you could have just looked at the exclusion question, seen what LSAT went with, and just gone in that direction. Usually the approach that they take for the setup tends to work out reasonably well. And if you don't have a good reason to go in a different direction, you may as well go in that one. So you'll notice that LSAC on that first exclusion question, they basically set this up based on the bikes. So they had the bikes locked in and then they assigned people to the bikes. Now, the way that this game works is that each of these bikes is going to be tested once on day 1 and then once again on day 2 by a different person. So we'll set this up as 2-tiered. The 2 tiers being, of course, day 1 and day 2. The people themselves are S, T, and Y. And the way that this game works essentially is that every single one of those 4 people is basically going to show up on each of the 2 days. So all of them will show up across day 1. So they show up exactly once. And then again, they will show up on day 2. So every single person tests 2 different bikes on 2 different days. And actually on that point, the setup also explicitly does note that a given person is going to test a different bike on the second day, which means that the same person can't show up twice on the same bike. So for example, if R is testing F on day 1, he's going to have to test one of the other bikes on day 2. So you can never have duplication kind of going down. From there, the rules themselves, essentially you should have something that roughly looks like this. We're told that R can't test bike F, Y cannot test bike G, T has to be one of the testers over here on day 1 or day 2. We just don't know which day. And lastly, the last rule. For the record, this last rule is actually the reason that this setup ends up working out a little bit better. Because by setting it up this way, the last rule effectively just gives you this block. Whatever you have Y on day 1 is going to have to be tested by S on day 2. So you end up with this very clean YS block. Now, that last rule should have stuck out a little bit because you'll notice that there's not a lot of possibilities for it. The thing is, the YS block, it can't really go into H because T has to be one of the testers there, and they can't go into J because Y can never go into J, which means that your YS block ends up having to go into either F or G. And I mean, that's a quarter of your board right there. That's kind of significant. So it might not be a bad idea to exhaust the game just based on that YS block. If you can do more with it, that's great. But even if you couldn't, that's probably somewhat worthwhile. So what we'll do is we'll set up 2 scenarios. And yeah, we can either have the YS block over here, or we can have the YS block over there. And of course, this is also day 1, day 2. Now, in terms of can we go further, what else can we figure out here? We actually can end up doing a little bit more damage in the second scenario here, because you'll notice that R can't go into F. Now, in the first scenario, that doesn't say much because this is already blocked off regardless, so R can maneuver between any of these 3 spots. But in the second scenario, the fact that R can't go into bike F, but it also can't go into bike G because we're locked out, right? Essentially means that R can only go into H or J. And in fact, it's not really or, because we know that everybody has to test 2 of the bikes, which means that R does not do H or J. R is going to have to test both H and J. And that's actually a rather powerful deduction, because that means that bike H in this situation is going to have to be tested by effectively R and T. Now, we don't know which one's which in terms of the day, but we know that those two are going to take up bike H in its entirety. We also know that we will have to have an R somewhere over here with someone else, but we don't know exactly who. And beyond that, oh, actually, there's one more step we can take. We know that Y can't go into bike J, which the thing is, we still have to have another Y. We've taken care of one Y over here, but there's a second Y that we have to accommodate. And since it can't go into J and H is already full, the other Y is going to have to go into bike F. More specifically, it's going to be day 2 for bike F, because the Y for day 1 is already resolved. So that's also pretty good. From there, I guess, do we know much more? I suppose we can say that this F on day 1, there's a limited number of options. It could be an S, or it could be the other T. So I suppose we could say this is either S or T. So I guess that's something, but I guess from here it's a little bit more open. Now, the top scenario, unfortunately, is a lot more flexible. So R is going to go into 2 of these 3 bikes, but I mean, arguably any of them could work. Y can't go into J, but it can still go into one of these 2 spots. I suppose if you wanted to, you could put a little reminder here that you have to have a Y into one of those 2 slots, but we just don't know which ones. And of course, it would be a day 2 position, right? Because we know that day 1 Y is already taken care of. So from there, let's take a look at the rule substitution questions that we had. Question number 1. So see what you can do with this on your own once again first, and resume when you're ready. All right, so here we go. So the question itself. So the question is asking us to replace this rule that says that whatever Y does on day 1 would have to be done by S on day 2. Basically, this last rule that we had over here. Now, let's see. Answer choice A. If Y tests a bike, then S must also test that bike. Now, you'll notice that this goes too far. This never had to be true, because answer choice A would effectively apply to both bikes that Y tests, and that's not accurate, right? Now, the bike that Y does on day 1 has to be done by S on day 2, but there is another bike that Y tests, and that one doesn't have to be tested by S. So this never had to be true, so we can get rid of answer choice A. Next, if S tests a bike, then Y must also test that bike. And same thing, that's not true for both of the bikes that S tests. That's not a true statement about S in general. It's only true for the bike that S tests on day 2. So this goes too far. Answer choice C. The bike tested by S on the second day cannot be tested by either R or T. Now this, you'll notice that this is basically just a straight inversion that we were talking about before. Instead of saying that whatever S does on day 2 has to be done by Y on day 1, this just says that whatever S does on day 2 can't be done by anybody else, which of course then forces that to be Y. And that definitely had to be true. Whatever S does on day 2 couldn't be done by R or T because it had to be Y. And it would ensure that Y would go there because there's nobody else left. So answer choice C would be a viable replacement. Next, answer choice D. S cannot test bike H on the second day. Now, that's technically true. S could not do bike H on the second day because if S did H on the second day, it would force T to go over here, and then Y wouldn't be on day 1 for that. So this had to be true. That's fair, but you'll notice that this doesn't do all that much. The only thing it tells you is that S can't go on H on day 2, but wherever S goes, it wouldn't force Y to go on day 1. This doesn't really do all that much. So answer choice D is out. Answer choice E. Either F or G must be tested by Y and S on days 1 and 2, respectively. So let's start with, does that have to be true? Did we have to have either F or G tested by Y and S on days 1 and 2, respectively? And yeah, that was kind of one of the logical consequences, right? That you have to have this YS in that kind of day order, either on F or G. And the other question is, does it get the job done? Well, yeah, because if we have to have Y and S on days 1 and 2, respectively, on one of those 2 bikes, then we will end up with that YS block. So this gets the job done, and it had to be true. So this is viable. Answer choice F. Y cannot test the same bike that either R or T test. Now, you'll notice that's not really true at all, because we know that Y could have gone with T, specifically the Y that goes on day 2. So we can get rid of F. That never had to be true. G, one of the bicycles tested by U must also be tested by S. Now, this is true that at least one of them did, but this doesn't get the job done because it doesn't tell us which one. Answer choice G would allow for you to have the bike that Y does on day 2 be tested by S on day 1, which is fine, but then it no longer forces you to have a YS block in this sequence. So answer choice G is not good enough. So the only answers here are C and E. Onwards, let's take a look at number 2. Now, once again, take a look, see what you can do with it on your own first, and resume when you're ready. All right, so question 2. Here we're being asked to replace this rule that says that R cannot test F. So now we're replacing this rule right here. Let's see what we can do. Answer choice A. F must be tested by Y and one of T or S. Now, first of all, I guess, is that true? Does F have to be tested by Y and one of T or S? And actually, yeah, because if you notice our our consequences here, the exhaustions, we always had a Y testing F, and the other person was always either S or T. So answer choice A, this had to be true. And then the other half of it, does it get the job done? Does it ensure that R is not going to test F? And actually, yeah, easily, because if it's got to be Y and one of S or T, then it's not going to be F. Answer choice A is rather viable. This would work as a potential replacement. Next, B. R must test both H and J. Now, this would get the job done because it would ensure that R cannot go into F. But the thing is, you'll notice that this didn't have to be true, because in the top scenario, we actually could have had R in G as one of your bikes instead. So since that never had to be true, this we can disqualify. Next, C. If S tests G on the second day, then R must test both H and J. So I guess one question, just on the simpler side of things, did that have to be true? And yeah, it did, because you'll notice that anytime S was on the second day of G, then yes, R did end up having to go into both H and J. The other side of it, though, is would this get the job done? Would this ensure that R never tests bike F? Now, in a situation where S does go on G on the second day, well, this explicitly takes care of it, right? Because then R would have to go into H and J, so it definitely would not be testing F. But remember, with conditional statements, you always want to make sure that you're aware of the consequences of both sides of the condition. Answer choice C only really tells us what happens if S is testing G on the second day. But then we want to be worried about what happens if S is not testing G on the second day. Well, you'll notice that if S wasn't testing G on the second day, then where would it go? And the only real place it could have gone is over here. It would have had to test F on the second day. But if that's true, then you would end up with the Y on day 1, because that YS block always has to be together, in which case you'll notice that R is still going to end up not testing F, which means answer choice C works. This would have ensured that no matter what, whether S is doing G on day 2 or otherwise, R is not going to test F, and it always had to be true. So this is viable. Next, D. Y and S must test F. Now this, you'll notice, never had to be true because we could have just as easily had a T here. So this, since it never had to be true, is a good enough reason to get rid of it. Answer choice E. If R tests J, then he must also test H. Now this arguably also doesn't seem like it had to be true, because if R tested J, well, in the top scenario, he could have tested J, and couldn't he have also gone into G, so he didn't have to go into H? So this already doesn't seem like it had to be true, so that's a good enough reason to get rid of it. Moreover, answer choice E only tells you what happens if R tests J. But what if R doesn't test J? Wouldn't this leave wide open the possibility that he could be testing F? And maybe. So either way, this doesn't work as an answer. Next, R must test two of bikes G, H, and J. And this one is worth noting is just another inversion. Instead of saying that R can't go into F, this is just saying that he has to test two of the other bikes, which then obviously means that he's not going to go into F. So this would work as an answer. It definitely had to be true that he had to test two of G, H, and J, and it would ensure that he would not be testing F. So this is another viable answer choice here. Lastly, G, only Teresa can test F with R. So if we implement a rule that says that T is the only person that can test F with R, now is that true? In a very roundabout way, I suppose that's true, because when you say only Teresa can test F with R, that means that the other people, such as Y and S, cannot test F with R, which is accurate in a sense. S and Y cannot go into F with R because, well, R can never go into F. So in a very technical roundabout way, I suppose G had to be true. But I guess the real question is, would this ensure that R is not going to go into F? And that it wouldn't. The thing is, if we say that only Teresa can test F with R, I guess the real question becomes, would it be possible for Teresa to test F with R? And it would, because the thing is, if we ran a scenario here, this answer choice would perhaps allow you to have, let's say, T and R over here, and then I suppose we could have our YS block over there. And yeah, otherwise there's no real issue, right? You could have perhaps a T with another R over here, or actually no, that wouldn't work because we're not allowed to have the Y on the last one. But perhaps we could have T and Y over here, specifically with the T on top, Y on the bottom. And then we could have R and S doing whatever over here. So in that sense, there's no reason that answer choice G wouldn't allow R to go into T. So we can get rid of answer choice G, and the only viable answers here are A, C, and F. All right, so just to kind of recap the general points. So as far as a good answer choice to one of these rule replacement questions is concerned, essentially you have two parameters that you're concerned with. First of all, does it get the job done? A good answer choice, and this is somewhat more obvious, but a good answer choice is going to ensure that whatever restriction used to exist is going to be maintained. If the original rule said something like X is always before Y, then a good answer choice will ensure that X is always going to be before Y. But in addition, you also want to make sure that an answer choice that you're looking at is going to be one that always had to be true. So if you're looking at an answer choice and it wasn't always necessarily true, then that's a good enough reason to get rid of it as well, because if you implemented that as a rule, it would go too far. It would over-restrict the game. Now, depending on the situation, one or the other parameter here might be a little bit easier to use in order to get rid of an answer choice. If you find that an answer choice happens to be especially restrictive, it's especially limiting, then my first thought would be to consider the second question, which is, did it always have to be true? Because if an answer choice is especially restrictive, chances are if it's wrong, it's because it goes too far. It's because it didn't really always have to be true. On the other hand, if you notice that an answer choice is especially open, it doesn't seem to have too much of an impact if it's not strong enough, then my first thought would be, does it really do what I need it to do? Does it go far enough to ensure that the initial restriction will be maintained? But once again, a good answer choice will meet both parameters. It's going to be something that ensures the initial restriction will be maintained and something that always had to be true.